Good morning, all of you. So, in the previous class, we discussed about solenoid and toroid. And so now let us see the force between two long parallel current carrying conductors. So that means the magnetic force between two long parallel current carrying conductors. Now we need to discuss in this class. So between the two charges, moving charges, we already calculated the magnetic force in the beginning of this topic, right? And so now in a similar way, there exists some magnetic force between the current carrying conductors also. We need to calculate that magnetic force between two current carrying conductors here. So these are long current carrying conductors. That means we may say like infinitely long current carrying conductors. That means when compared to the distance between them. So now here I am assuming like two long parallel current carrying conductors are placed like this, right? And so I am taking this current as I1 and this current as I2. And separation between them as D. So this is a current carrying, that means separation between them. So that is the case here. Now first let us discuss why this magnetic force will arise here, right? So that means first I am explaining how this magnetic force will act between these two current carrying conductors. Is there any electric force between those two current carrying conductors? Is there any electric force? So the important thing here is you need to note that we discussed already, we completed already about these two parallel charged particles here. That means if the two charged particles are moving like this is Q1 and Q2. And we discussed already here between these two there exists already electric force because they are having, that means those are the charged particles. So electrostatic force will be there. Like for example, if both are like charges, then electrostatic repulsive force will be there, right? And so now in addition to that, now in this topic we already calculated that magnetic force also there, and we already that means we already concluded that the net force between them will depend on the nature of the electrostatic force. If electrostatic force is repulsive, the net force between them will be repulsive, and if electrostatic force is attractive, the net force is attractive, because we concluded the magnetic force is lesser in magnitude when compared to that of electric force. We derived that ratio also there. Now like that, what I am asking is, in this case, when in case of current carrying conductors, is there any electric force between those two current carrying conductors? Is your answer yes or no? So your answer should be no, because there is no any charges for this here. That means there is no any charge given to the conductors, either first conductor or second conductor. Is there any charge? Is there any carrying some charges? No. Then your question will be how current is flowing. That current is flowing because of charges only, right? So that current is flowing because of the charges, but the net charge of this conductor will be zero. We are not giving any excess charge to the conductor. So you should remember that whenever current is flowing through the conductor, the charge of this conductor will be zero only. So only the whatever the charges available in that, and that means the free electrons, conduction electrons, those will accelerate because of this electric field. So that means we are not adding any charges to that, so it doesn't possess any electric charge. So those are electrically neutral. The current carrying conductors are electrically neutral, and so that there is no any electrostatic force is not there between those two current carrying conductors. That is the first thing you need to note that here there. So there is no electrostatic force between the two current carrying conductors. Now the magnetic force will arise. So now let us see how that magnetic force will arise. So for this we need to use the two concepts there. One concept is current carrying conductor produces a magnetic field. That is one concept, and we know already how to find this magnitude and how to find the direction. The magnitude means this is an infinitely long conductor, so the magnitude you can write it as mu naught I by 2 pi r, and whereas the direction means we can use our right hand thumb rule here. With the help of that you can find the magnitude and direction. And the next concept you need to remember here is, whenever a current carrying conductor is placed in the magnetic field, there exists some force acting on the current carrying conductor, and we know already how to calculate that force. That means dF is equal to, or F is equal to BAL sin theta you can write, and the direction of that force can be found by using this Fleming's left hand rule, right? By using this Fleming left hand rule, you can find the direction, or by using cross product also you can find the direction there, right? So now those two concepts we need to use here. So remember those two concepts there. Just I explained now. We discussed it already, and we solved so many problems based on that. And so now let us find the direction of this magnetic field produced by the first conductor in the region of the second conductor here, right? That means this conductor is carrying, first conductor is carrying some current. So now it is producing magnetic field in the surrounding of that. So that magnetic field I am calculating here. So this magnetic field will be, say, this side it will be into the plane. So I am naming it as B1. So then B1 will be into the plane, right? So the magnetic field will be into the plane. Now what we can say is this conductor is lying in this magnetic field. So that is an external magnetic field here. That B1 is an external magnetic field for this I2. And so that there will be some force acting on this I2 here. And so that force direction now we need to find here. Magnetic force is acting here. So for that we need to use this left hand rule. In this, forefinger is field, central finger is current direction, and the thumb gives the direction of the force. Now let us apply here. So all of you stretch your fingers and try to apply this for this case here. Field is inwards. So the field is inwards and current is flowing upwards here. So the current is like this. Then the thumb is towards left, right? And so that means here this force will be along this direction. So now I am taking this as F21. So force acting on 2 due to this 1. So that is F21. I am taking that force here. Next, similarly, the reverse assumption, now reverse we need to consider here. That means now this conductor is also carrying some current. So that also produces some magnetic field. So now let us identify the direction of that magnetic field in the region of this first conductor. So because now this conductor can be assumed to be lying in the magnetic field here. So that means now the current is flowing in upward direction. So here the field lines will be this side, they will be coming out here. So the field lines are coming out there. And so that here once the field lines are coming out, that means magnetic field will be out of the plane. Magnetic field B2 means magnetic field due to this I2, second conductor. Now again let us identify the direction of this magnetic force here. The direction of magnetic force. So the field is out of the plane, current is flowing in upward direction, right? So field is out of the plane, current is upward direction. So this will come here. And so then this will be F1, 2. Force acting on 1 due to this 2 we can write there. Right? So that will be that force here. And so next here what we can write here is, let us write now all these expressions here. The magnetic field due to this first conductor and magnetic field due to the second conductor. So let us write all those expressions here. Magnetic field due to I1 at I2. That means at I2 means in the region of the second conductor. So then this value we are taking it as I1, B1. So simply what we can write is mu naught I by 2 pi d we can write. Because it is an infinitely long conductor. So for infinitely long conductor you know that. And so now here similarly the magnetic field due to this I2 at I1. So this will be B2. So in a similar way you can write mu naught I2 by 2 pi d, right? Those are the magnetic fields. Now the force acting on a conductor of some length L we are assuming here. That means force acting on this conductor we are finding here. So let us take this. Generally in these problems we express like force per unit length, generally we express there. So once you started the numericals then you can find such a sentences there. So generally we define the force per unit length. And so now I am taking a small element like L length I am assuming. So force acting on that length I am writing here. So this is not the whole conductor here. Whole conductor length is infinite only. For this small element we are taking there, that length L. So that means now force acting on second conductor due to first one. So this value what we can write is F2 is equal to, that means F21 B1 into I2 into L. BAL sin theta you need to write here. That theta value you can write as 90 degrees. Because here we mentioned already field is into the plane and current is flowing upwards here. Angle between them will be 90 degrees. And therefore this F21 you can write this expression as F21 is equal to B1 value you can substitute there, therefore mu naught I1 I2 by this 2 pi d. So that will be that F21 value there. So next let us write this force acting on first conductor due to the second. So due to the second conductor. So F12. So F12 what we can write is now magnetic field is B2, now current is I1 and its length is L and same sin 90 you can write here. Therefore this F12 what we can write is B2 value you can substitute by using this. So mu naught I1 I2 you will get again there. So here into L. So mu naught I1 I2 by 2 pi d into L. So now you can observe these two expressions here, F21 and F12 values, both are numerically same, right? So both the forces are numerically same, and so then you can conclude that the magnetic force acting on those conductors will be equal in magnitude and opposite in direction, right? And so that we conclude that force between the two conductors is given by this expression here, right? And so I can write this as therefore this, that means F1 is equal to, here F12 is equal to F21 and therefore which is given by mu naught I1 I2 by 2 pi d into L. And so now here what we can write here is, therefore what we can conclude is the magnetic force between two parallel conductors, that means two parallel current carrying conductors there, so is given by F is equal to mu naught I1 I2 by 2 pi d into L. So we can generalize that formula now like that. The magnetic force between those two conductors you can write like this. The magnetic force between two parallel current carrying conductors can be expressed as by using that formula there, right? And so as I said, in general we express that as a force per unit length there. So if you are expressing in terms of force per unit length, so force per unit length, so that we can write this as F by L. So F by L value is mu naught I1 I2 by 2 pi d. So now this we express in terms of this force per unit length here, F by L value. So now this unit is Newton because it is a force, and this unit we express like Newton per meter because we are writing that as force between force per unit length there, right? And so just mention that and actually that is one of the fundamental unit in SI. And so now in that the ampere is defined by using this formula only. The definition of this ampere, for the all these fundamental units, there will be some standard definitions will be there. And so like that, the ampere definition is defined by using this formula only there. And that is nothing but simply the ampere definition means what we can write here is so ampere definition here. So the ampere definition is nothing but if I1 is equal to I2 is equal to 1 and D is equal to 1 meter, then F by L is that means this value is nothing but 4 pi into 10 power minus 7 and into this is 1 into 1 you will get, by this is 2 pi into 1. So this value is nothing but what we can write is 2 into 10 power minus 7 you can write there. 2 into 10 power minus 7 Newton per meter. That means now this definition is defined as That means if the current, if two parallel conductors are separated by a distance of 1 meter, and if the current flowing between them is such that means current flowing in the conductors is such that the force between them is equal to 2 into 10 power. Force per unit length between those two conductors will be equal to 2 into 10 power 7 Newton per meter. Then the current flowing through that conductors is said to be an 1 ampere. That means we allow some current flowing through both the conductors, and generally we allow them same amount of current is flowing through them, and we adjust the current value until the force between them will be equal to 2 into 10 power minus 7 Newton per meter when they are separated by a distance of 1 meter. Then the current flowing in the each conductor is nothing but we define it as 1 ampere. That means here you may get confusion. I am already taking this I1 and I2. Actually, while defining that, we adjust the strength of the currents there. We adjust the strength of the current such that means just I am showing here, if they are 1, then the force will be equal to 2 into 10 power minus 7 Newton per meter. So while defining, we adjust the strength of the current flowing in that two parallel conductors until the force between them is given by this expression here. So then the current flowing through that each conductor is nothing but we define it as 1 ampere there. That is the definition there. And you may mention that may be there in our books, or just mention the definition there, ampere definition. When the two long parallel conductors carrying identical current, carrying same amount of current, repel or attract each other with a force of 2 into 10 power minus 7 Newton per meter, with a force of 2 into 10 power minus 7 Newton per meter, then the current flowing in each conductor, is said to be 1 ampere. Right? So it is the definition of this ampere, or the standard definition of this ampere. And next here we may mention some points here, whether that force is attractive force or repulsive force here. So just by using this here, by using this diagram, you can conclude that now the force between them is attractive force, right? So we can conclude that as when current is flowing between them in the same direction, that means when the current in both the conductors is in same direction, the force between them is attractive force. And now if the current is in opposite direction, so now let us check for this opposite direction here. When current in these conductors is in opposite directions, now I am taking here. So this is I1 and I2, and suppose they are same separation here, just we are finding the direction. The same process. So this will produce some magnetic field. So let us identify the direction of magnetic field of I1 at the site of I2. So that means now this I1 is flowing here, so the magnetic field will be there like this. So here the magnetic field will be into the plane, I can write. So that means now here this B1 is into the plane, right? And so now similarly, now let us find the force here. The force acting on this I2, let us find here. So the force acting on this I2 is nothing but field is into the plane, current is in downward direction. So apply this, all of you stretch your fingers and apply this so that you will get the clarity here. Field is into the plane, current is flowing in downward direction, so thumb you will get towards right. So that force acting on this will be along this direction. This is F21, force acting on to due to 1. Next, similarly, let us find the magnetic field produced by this I2 here. So the magnetic field produced by the I2 will be there like this. Now the current is in downward direction, so here the magnetic field is into the plane. So here the magnetic field is into the plane. So B2 is also into the plane here. Now again let us find the direction of this force here. So the B2 is into the plane, and now the current is flowing in upward direction here. The current is flowing in upward direction, and a B2 is into the plane. So this force will be along this direction here, towards left you will get. And so that this force will be, say, F12 will be along this direction. And so now we can observe that this force is nothing but there, because of this force the wires will try to move away from each other. And so that force is nothing but we call the repulsive force there. So we can conclude that the force between them is attractive when the current is in the same direction, and force between them is repulsive when the current is in opposite direction. So just mention that points there. The magnetic force between the conductors, the magnetic force between the two parallel conductors will be attractive, if current in the same, if the current in the conductors is in same direction, if current in the conductors is in same direction, and that will be repulsive, when the current in the conductors is in opposite direction, you may draw both the diagrams there. This is attraction and this is a repulsion case. Draw both the diagrams there. And also mention the one more point there. There is no electrostatic force between these two conductors. There is no any electrostatic force between these two conductors. That means only the force existing there is magnetic force only, right? And so now generally the another theoretical question they will ask like what will be the direction of, that means what will be the force, nature of the force if the conductors are not parallel to each other. So here I discussing like when they are parallel only. Now let us take the case if the conductors are not parallel. So one conductor I am taking like this and other conductor I am taking like this. Or let us take one conductor is there like this and other conductor is also like this. Right? So now like this I am taking here. Let us identify the directions in those three cases here. Suppose this is figure A, and so this is figure B, and this is figure C. So now let us answer the direction of the force, whether that is attractive force or repulsive force in those three cases. So just let us apply the, follow the same procedure how we decided the direction there. So here I am taking this, this magnetic force will be say into the plane here. The magnetic field produced by this will be into the plane. So that means here this is B1 I am taking. Suppose say all these are I1 and I2. So then it is B1 that is into the plane, right? And so now let us identify the direction of force acting on I2 due to this field. Field is into the plane and current is flowing like this. And so now the force will be along this direction. So the force acting on this will be along this direction. This is say F21, force acting on to due to 1. Now again let us identify the magnetic field produced by this conductor here. So this magnetic field will be there out of the plane here in this region. The field lines will come out like this. So this magnetic field here will be out of the plane. So this will be B2. So B2 is out of the plane. Now let us identify the direction of this force. The direction of the force means now it is field is out of the plane and current is flowing like this. So that force will be there now along this direction here. So that means now this force will be along this direction like F12, right? And so now again you can observe that because of that force, the conductors, or if they are ready to, that means if they are free to move, they will approach each other. The distance between them is decreasing. And so then you can call that as an attractive force there. So that means in this case the force will be attractive, right? So that means here you can write that force as attractive force. Now let us think about this case here. For this case, when the currents are in downward direction here, same approach. We need to take field directions and we need to decide the direction of the currents there. So that means now here this current is inward direction, that means downward direction here. So the magnetic field there is out of the plane. So B1 is out of the plane. And so now let us take this direction of the field is out of the plane and current is flowing like this. And so now the magnetic force, and this current is like downwards and the field is out of the plane. So the force will be along this direction. And so force will be along this direction you will get. This is F21. Now similarly the magnetic field produced by this conductor, if I consider I2, the magnetic field due to I2 at the side of I1 will be into the plane. This side the field lines are coming into the plane. So here this is B2 is into the plane here. So now let us identify the direction of the force here. Field is into the plane, current is in downward direction there, right? Field is into the plane, current is in downward direction, so the force will be along this direction. And so that this force will be F12 will be again along this direction. So again you can observe that because of that force they will attract each other, because of that force. And so that means here this is again attractive. And so now let us consider this case now. So if you are considering this case, again let us take this magnetic field direction here. So due to this I1 I am writing here. So the field lines are coming out this side. So from this side. So here the magnetic field B1 is out of the plane. Now apply the left hand rule and identify the direction. Field is out of the plane and current is flowing along this direction. Then you can observe that force you will get like downwards, perpendicular to the conductor and downwards. And so then this is along this direction here. F21, right? And then next let us consider this this conductor here. Let us take this conductor. The magnetic field produced by this conductor will be out of the plane, you will get the I2 magnetic field. The magnetic force field will be out of the plane. So that means here B2 will be out of the plane here. Now let us find the direction there. So let us find the direction of this magnetic force. Field is out of the plane and current is field is out of the plane and current is flowing downward. So this will be the direction of the force acting on I1. So that means the force acting on this I1 will be along this direction. So now you can observe that in this case now because of these forces here the conductors will move apart from each other, right? And so that then you can say that this here the force will be repulsive force, you can write here. So it is now this force is repulsive force, right? So that will be the repulsive force here. And so next here, that means from this actually what you can conclude here is when the currents are such that whether they are both are converging or both are diverging. Now you can observe that means converging or diverging means in light rays generally we use that converging and diverging. So here the current will appear like that only. They are starting like this and they are moving away from each other. The separation between them is increasing. Then I am saying that as converging currents. And if the currents are approaching like this, if the distance between those two conductors goes on decreasing, so then that is nothing but I am saying it as a converging here. So this is the diverging and this is the converging currents. So if both are converging and both are diverging, then force between them is attractive. So you can observe in both the cases. This is the diverging case, we are getting attractive, and this is the converging case, we are getting attractive. And this is in this one is converging here and other is diverging here. So then we are getting that as repulsive. So just you can remember it easily like that. So mention that there. In case of non-parallel conductors, the magnetic force between them will be attractive. The magnetic force between them will be attractive when the current in both the conductors is either converging or diverging. And this force will be repulsive if current in one conductor is diverging, and other is diverging. That means one is converging and other is diverging. So just to draw this diagram also so that you will get the clarity about that. What is converging and what is diverging. So based on this force between the parallel conductors, lot of questions will be there. So for all of them the basic approach will be same thing what I explained here. We need to follow like this. Magnetic field calculation and then force calculation. You need to identify the directions there clearly, right? And so then here you can also mention one more note like if suppose sometimes they will ask a question like suspending here or magnetic levation, like suppose just let us mention it as another point here, like I am taking this this one conductor is rigidly fixed like this, right? Now the other conductor is placed above this. Say suppose say I1. Now this is placed above that at some separation of D. Now suppose here the given condition is this wire will remains in equilibrium. It remains in equilibrium means just that support is not required, or if suppose if you are assuming that this wire is suspended by using some say some strings, the tension in the string will be 0. That means support is not required for that wire. Then what should be the direction of the current and how much current should flow in that? So generally the questions will be there like this. Is it clear? This will be a fixed conductor and it is carrying some current I1 along this direction. So now I am asking that if this above wire second conductor is remains in equilibrium in air, remains suspended in equilibrium in air, then what should be the direction of the current and then what should be the current value, how much current should flow. And so now here for this type of problems, it remains in equilibrium means without any support, just this weight of this wire should be balanced by some other force. That other force is nothing but here magnetic force. And so now this magnetic force direction definitely must be away from here. This magnetic force must be directed in upward direction there. So magnetic force is in upward direction, that should be repulsive. That force should be repulsive. And so that force is repulsive means then you can conclude that current must flow in opposite direction here, right? So just mention that point here or write that as a note. If one current carrying conductor is fixed horizontally, between two rigid supports, and it carries a current I1. That means the current flowing in that wire is I1. That means some connection will be there. I am not showing that circuit. Just I am showing that wire here, fixed wire. Some connection will be there in that circuit. That is not required for us. The another wire is placed above it and parallel to it such that it remains suspended in equilibrium. So it remains suspended in equilibrium and that automatically indicates that no support is required there. It remains suspended in equilibrium at separation D. Then current in that conductor must be opposite to that of I1, and its value can be obtained by using following equation. So in equilibrium what we can write here is this magnetic force must be equal to mg, right? And so now this magnetic force what we can write is we derived an expression here, mu naught I1 I2 by 2 pi d into L. So this is equal to mg. And here generally that is what I said here, we express in terms of this m by L, that means this force per unit length. So generally for this type of problems they will give the data mass per unit length of this suspended wire there. So that we express in terms of this m by L like this. Is it clear? So now this will be the force per unit length, and now this is also now mass per unit length into G, that gives the force per unit length. So generally for these problems they will give this data here. So by using this equation now we can calculate this I1, I2, or if they ask separation D by giving I1 and I2 values, you can do those calculations there, required calculations you can do by using this equation there. So now in the same case if they ask like if the wire is placed below this is I1, now instead of placing above this, if the wire is placed below this, then is there any difference here? In this case the conditions are same. Now this wire remains suspended in air. this wire remains suspended in air. So what should be the current or what should be the separation required there? So that means now in this case it should be remained suspended in air, means now again it should be the magnetic force should be should balance this weight of this wire here. So now weight of the wire is again in downward direction, and so now the magnetic force should be in upward direction, right? And so now this diagram is same here and here, but here this force now we say the repulsive force, and so that the direction of the current must be opposite each other in both the conductors. But here this force should be the attractive force between these two conductors here, right? So this force should be attractive force, means now I2 should be in the same direction of this I1 here. So that is the important thing, or that is the difference between those two cases here. Remaining everything will be same. So if you are balancing this force here, so that means everything will be same here. In equilibrium, again this Fm we can write this as mg, and so finally directly I am writing this final equation here, mu naught I1 I2 by 2 pi d is equal to m by L into g. So if m by L is given, I am writing this. If mass and length are separately given, then you can keep L this side only. That depends on our given data there. So just to mention that in the above case, after writing this, then you can mention this diagram and you can draw this. In the above case, if the wire is placed below the fixed wire, if the suspending wire is placed below the fixed wire, if the suspending wire is placed below the fixed wire, then current in both the conductors must be in same direction. Then current in both the conductors must be in same direction. And so then note that equations there for this also, the same equations. And next, instead of giving this in case of a fixed wire, generally they may give like it is placed in a magnetic field, like as I said, Earth's magnetic field, and what should be the magnetic field required, they may ask there. So here also you can mention that. I think we discussed already that point. That means if a wire is suspended like this, a wire is say placed along east-west direction there. Suppose say current is flowing towards east direction here. Now BH is given, S horizontal component of magnetic field is given. So then how much current is required to suspend this wire in equilibrium without any support? Remains suspended in the sense without any support. So now here the magnetic field, Earth's magnetic field will be BH direction. We already discussed it when we were discussing about the neutral points. The BH direction is from geographical south to geographical north. That is the direction of the BH. So BH is along this direction, and this is the east direction if you are taking. Then current is along this direction and field is along this direction. And so now force is in upward direction here. So that means if required current is there, then this can balance the weight of this wire here. So such a type of questions may also be there. So just mention that point again here. So this is one point here. The next let us mention this another point here. If a current carrying conductor is placed along east-west, and a current is flowing towards east, in the Earth's horizontal component of magnetic field BH, in Earth's horizontal component of magnetic field. Horizontal component of magnetic field means we represent with the BH. BH means horizontal component. The effect of vertical component will be there, that we will discuss it later. Only horizontal component I am taking here. The Earth's horizontal component, in the Earth's horizontal component BH. If this wire remains suspended in air, then the current that should current flowing through the conductor is given by, so now for this also this magnetic force must be equal to mg, right? But here the magnetic force is not between the two current carrying conductors as that of this case. It is because of the force acting on a current carrying conductor when it is placed in a magnetic field. So when it is placed in a magnetic field means we can write this as BH into I into L into this will be sin 90 we can write. Just BIL formula here, BIL sin theta formula here. Is it clear? Only one conductor is there, that one conductor is placed in external magnetic field, that means Earth's magnetic field. Earth is producing some magnetic field, so then its horizontal component we are taking there. So that is equal to mg you can write. And so from this current required we can write this as mg by bh into L required for this case. Or sometimes they may give some angle there, that means it is making certain angle theta with the east direction. It is like suppose it is placed along northeast. If the conductor is placed along northeast, then angle between L bar and B bar now we need to take there. Is it clear? If the current is along this current carrying conductor is towards east, then what we are taking, they are perpendicular to each other, so that I am taking this 90 degrees here. If it is placed along northeast direction, then 45 degrees will be there, angle between B bar and L bar. So that you need to remember there. So if theta angle is given, then that theta angle we need to consider here. That means that theta is we need to consider there. Or if you want, you can mention this here. If the conductor is placed in horizontal plane, just mentioned in the above case, then everything will be same. Just we are taking conductor is making certain angle theta, or just mention that in the above case, if the conductor is making an angle theta with east, then the current required to balance the weight of the wire is given by so see here, this is east direction and this is the north direction, west and south. Now here what I mentioned here is the current carrying conductor is placed like this. This is a current carrying conductor here. It is making an angle theta. Now our BH direction will be along this direction here. BH is, I will draw some big diagram so it will be clearly visible to you. So this is east, north, west and south. So now I am taking that what I mentioned there is this current carrying conductor I here, it is making certain angle theta. And so now here this BH direction will be there along this direction here. This BH is along this direction. The Earth's magnetic field is, as I said, it will be from north to south, it will be. Sorry, south to geographical south to geographical north. The direction of that BH will be. And so now we need to write this expression as 90 minus theta we need to write here. That is equal to mg. BIL, the angle, this angle you need to write here. This angle will be 90 minus theta. The angle between B bar and L bar you need to write. L is nothing but this vector here. I into L, DL, current element we need to consider. So then this B bar is along this direction. So if it is making an angle theta with the east, then here angle will be 90 minus theta, you need to substitute there. And so that this equation you can write this as, from this I is equal to mg by bh into L into cos theta you can write. That means simply I am giving one case here. They may give that if theta is given with the north direction directly, then you can take that sin theta directly there. That means generally, you know, in these cases they will express like 30 degrees east of north or 30 degrees north of east. They will express like this. I think all of you know how to identify whether it is north of east or south of east angles there. So if it is given, for example, 30 degrees north of east means 30 degrees north of east means with respect to east, the conductor is placed at 30 degrees like this. Then that 30 degrees north of east means, then this will be the case here. That means with respect to east, the conductor is lying on the north side. So if it is given like 30 degrees east of north, so with respect to north side, this is the north side here, with respect to north side, then 30 degrees you need to consider towards east. So this is, we express this as, the first case we express this as north of east. That means 30 degrees north of east means this one. And this is 30 degrees east of north means this one. So 30 degrees east of north means we need to represent like this. 30 degrees north of east means we need to represent like this. So now here you need to take, in this expression you need to take angle between BH and this conductor. That angle you need to consider there, right? And so then based on this, as I said, based on the force between the two current carrying conductors, lot of problems are there. So then numericals I will explain in our next class, right? Thank you.